Okay, on example number 3, I'm kind of telling you that I want you to use the direct comparison test. So you have this big square root, a bunch of stuff. Hopefully you can see it's really not any type of our series that we've had so far. So again, just kind of ignore all the numbers and get it down to, let's see, you have n over n squared, which would be 1 over n. So I'm going to compare it to the series of 1 over n to the half power. So what is that? That's a p-series where p equals 1/2, which is less than 1, and so I know it diverges. Now because I've been asked to use the direct comparison test, I'm going to take what I'm comparing it to, which is 1 over the square root of n, because the square root of 1 is 1, and that has to be smaller than the square root of n plus 1 over the square root of n squared plus 2. And yes, you can separate those square roots. So I have to show that inequality is true. So let's go over that. Why is that inequality that way? Because this diverges. This is really big. Then I need this to be even bigger for it to agree on the divergence. Okay, so again, I'm going to cross multiply, keep that square root, so I have n squared plus n. Is this really bigger than the square root of n squared plus 2? Well, it is true as long as what? Okay, these are the same as long as n is greater than or equal to 2. So it doesn't quite hold true when n is equal to 1 for the first term, but it is certainly eventually true, and not too far out eventually, just when n is greater than or equal to 2. So I can still conclude that the series also diverges by the direct comparison test. Okay, so again, what did I compare it to? A known series, and I've written out what that known series is, and then for the direct comparison test you have to show that that inequality holds. Okay, so now in example number 4, hey, that's the same problem. So I know what the answer is, but now I want to use the limit comparison test. So again, I'm going to compare it to the same thing. So I'm going to say p equals 1/2, which is less than 1. So I know that diverges. But this time I want to take the limit as n approaches infinity, and remember what you pick goes on the bottom and what you are given goes on the top. That's the easiest way to keep everything straight. And then again, you're going to have all those fractions, so we're going to flip and multiply. So again, this goes up here, but the reciprocal. So you're going to have the square root of n squared plus n divided by the square root of n squared plus 2. What's that limit? Well, looking at these are the same. You have the same square root, so you have the same power of the same power, and so you have just the leading coefficient, so that limit is 1. So that's a finite positive number, so therefore the series diverges by the limit comparison test. Okay, so this is side by side how the direct comparison test and the limit comparison test differ. Not by much. You still have to take a known series and compare them. Just to tell you, most of the time the limit comparison test is a little bit easier. Alright, let's look at number 5. 1 plus the cosine of n. Now we've had n pi before, but not just the cosine of n. Well, if I got rid of that cosine of n, wouldn't I just have 1 over n squared? So I'm going to compare it to that, because I know p is 2, which is greater than 1, so I know this converges. Do I really want to do the limit comparison test? I'm going to try the direct comparison test. So I'm going to take what I've picked, and since it converges, then I need to show that 1 plus the cosine of n over n squared is what? If that converges, you need to show that this is even smaller. So I need to show that that is a true inequality. Well, one thing you should observe is that the denominators are the same, so we just really need to look at the numerator and ask ourselves, is 1 plus the cosine of n always smaller than 1? Well, if I subtract 1 from both sides, is that true? No. Cosine goes from -1 to +1, so it's not always going to be smaller than 0. So this is not true. So the direct comparison test, really didn't work for us. Or did it? Think about the cosine of n. Could I make that change somehow to make it true? Well, what if I come up here and I say, let's compare it to 2? Remember, we can write this as 2 times 1 over n squared. That's still a p-series. It still converges. It just converges to some value multiplied times 2, which is still finite. So let's see if I could change that up a bit. So if I made this a 2, and then I compared the numerator, and I have that, and I subtract 1, I would have that. Is that true? Yes, it is. And so we can therefore conclude that the series does converge by the direct comparison test. Now that's tricky. I can't tell you how to get better at these except for just keep trying. Could you have used the limit comparison test? Maybe. Give it a try and let me know if it worked out. Look at number 6. Wow. Okay, so the highest exponent here is 5n cubed. In the bottom, I think that would be n to the 5th. So if I reduce that out, I would have n squared. Now the question is do I need that 5 or not? I don't know. So I'm just going to try 1 over n squared and see if that works, because I know that p is 2, which is greater than 1, so this converges. Do I want to use the direct comparison test? No, I think I'm going to use the limit comparison test. So I'm going to take the limit as n approaches infinity of what I've chosen to compare it to goes on the bottom, and what I've been given goes on the top. And again, let's flip and multiply. So we're going to multiply this reciprocal on top. So you would get 5n to the 5th minus 5n cubed, all divided by this ugly thing. Okay, so again, the highest power down here is n to the 5th, n to the 5th. So we have the same degrees, so it's going to take the limit, just that leading coefficient is 5. Now just to tell you, you could have kept that 5 there, and that would have made a 5, and then you would have had a 5 in the denominator, and then your limit would have been 1. Same answer. You get a finite positive limit, and so therefore we can conclude that the series converges, because remember it always is going to agree, and we use the limit comparison test.